And write down time, 3:04. Okay. And I'll kind of say the same thing that, if you have another question for me, shoot it out in the chat room. Although I did write down three of them from the last section here before we took a break. And they were all from chapter 22. And they were number 54 and then 39 and then 49. So unless you guys have other thoughts, I will.
You did 51 this morning, right?
Go down that road. 51. We did, yeah. Yeah, we did 51.
Okay. I can look at the recording.
Okay. Yeah. If you don't mind, that would be best. We can cover all these other three.
Mm-hmm.
Yeah. And you'll see the video. That was the second one we did in the morning section. We did 50. That was a long one, the 50. Yeah, in fact, I'm looking back here. Number 50, we started at 10:10 and we started 51 at 11:08. So that was 58 minutes before we started the next one. I remember that one. All right. Well, so that I don't chit chat too much and we'll get us started here. Let me write down chapter 22, number 54. Oh, and let me turn camera back on and unlock it. See if it'll unlock. Okay, good. It did. All right. Let me go to screen sharing here. Nice. Okay. And let's log it in here. Let me try to find number 54. Oh, yeah, this is the chapter 22 where two of the pages didn't copyright. Let me go to the second one, 50. Oh, that's not it. Let's go to the other one, 54. Here we go. All right. So let's give this one a shot here. Number 54. Looks like it's got a PV diagram below it. Maybe I'll just draw that out first. It looks like we've got volume listed in liters. Okay. And it looks like there's a 10 liter and a 50 liter. Looks like they're calling this point C. And that is at a pressure of 1, and then this is in atmospheres. And it looks like straight above it, a pressure of 5 atmospheres, point A. And point B, looks like it's at 50 liters. It looks like an arrowhead up, so it must go from C to A. Then from A to B, and then from B to C. And obviously A to C is isovolumetric, and obviously B to C is isobaric. This one looks like, it says isothermic. Okay, so never be real sure till you read it, whether it's constant temperature or adiabatic. But they say constant temperature there. All right, so here's our cycle. Just 3 steps here. It says a 1 mole sample of an ideal monoatomic. Okay, so monoatomic, let me just point out then that CV would have 3 degrees of freedom. CP, then we would add 1 R, so 1.5 plus 1 makes 2.5 R. All right, and then gamma, which would be the CP over the CV. Although we don't have adiabatic, so I'm not thinking we're going to need gamma, but maybe I'll just put it here, would be 5 over 3. Okay. So a 1 mole sample of an ideal gas is taken through the cycle as shown. The process A to B is a reversible isotherm expansion. Calculate A, the net work done by the gas. B, the energy added to the gas by heat. C, the energy exhausted by the gas as heat. And then D, the efficiency of this cycle. And E, explain how this efficiency compares to the Carnot engine operating between these same 2 temperature extremes. Well, that's pretty good. Now, they asked a lot of questions. I don't want to go overboard on this, but maybe since, you know, this really isn't a timed activity, and the more I do, maybe the better. So maybe at the risk of doing too much, maybe I'll just put a little chart here that says A, B, and C. What is the pressure, the volume, and the temperature at each spot? And then also from A to B, and then B to C, and then C back to A. Why don't I put what is the change in internal energy? What is the heat? What is the work? And maybe even below this, I'll go net. All right. And so maybe I'll start with the easy one. I know that the numbers are really listed in this graph. I suppose we can decide what units to use. Maybe I will do units of pascals and volume in cubic meters. That's kind of my go-to, especially when you're asking about energies. Which means I've got to change my numbers here in the graph. But let's start with A. A's up here, and A says a pressure of 5 atmospheres. So grabbing my calculator and going 5 times 101,300, I get 506,500 pascals. It also says here on the graph, the volume is 10 liters. And noting that there are 1,000 liters in a cubic meter, I'll divide by 1,000. And so that's 0.01. And in fact, all those pressure and volumes are given. So I can do the same thing at B. This would be 101,300. And this would be 0.05 for the volume. Whereas C would have a pressure of 101,300 and a volume of 0.01. And remembering that PV equals nRT, meaning the T is PV over nR. And they said at the very beginning, this is 1 mole. So given any 2 of these, I can get the third. So I can get the temperature here. So I'll go with straight here. I'll go with A and go pressure, which is already in my calculator, times a volume of 0.01, divided by the number of moles, which they said 1. Let me just confirm that. Yeah, 1. And then R, which is 8.31. And so we're looking at a temperature of 609.5 on the Kelvin scale. Okay. Now, there are a couple ways I can do B. I know they said it was an isotherm, so that's probably the easiest way, just to say it's going to be the same temperature, 609.5. But I can also see it in the math. Look, the pressure dropped by a factor of 5, but the volume went up by a factor of 5. So if I put it into my calculator, this would go down by 5, that'd go up by 5, would still multiply out to be the same thing. Now, the one that has a lower temperature, a different one would be C, and it looks like it would be 5 times lower because the pressure dropped by 5 than the volume. So I'll just divide by 5 and write it as 121.9. But maybe I should also just confirm 101,300 for the pressure times the volume divided by the number of moles, which is 1, and divide that by 8.31. And sure enough, 121.9. So I don't know if I'm going to need all those temperatures. I bet I am, just because they asked for so much information. And so I thought, well, maybe I'll just fill out what I do know. But I also thought I would use this as an opportunity for you guys. It's a learning opportunity. And so obviously on a time test, you don't want to necessarily, let me write this down, number 22, number 54, don't want to necessarily do unneeded calculations. But for us, this might be good for us just to do what we do know. Because this gives me a chance to talk about the energy ones. my logic is this: go for the easy ones first, because you know these two added together give you that one. So if you know we need two of these, you got the third. And so might as well make the easy ones go first. And so things like delta E. Delta E is zero when there's no temperature change, because the internal energy is related to the kinetic motion of them. So I would say, do I have any isotherms? And yeah, A to B is an isotherm. So A to B would be zero. Now, also another thing is if you go through a complete cycle, all three of these should add up to zero. Now, that's helpful because, again, you only have to find one of these and you have the other one. But I know that because, again, if it gets back where it started, it would be at the same temperature, the same pressure, the same volume. In other words, the molecules would be doing exactly the same thing when they got started. So if they started at A and then went through a cycle and finished at A, you know that the change of the energy, they're back where they started. And energy is a state function. Now, heat and work are not. In fact, you hopefully they aren't zeros here. You're going to have like an input of heat and then an output of work. That's the whole idea of building an engine. So you want this to be a positive number and this to be a negative number. They have to be equal and opposite. They have to add to zero. Okay, now Q is zero in the adiabatic process. We don't have that in our problem. So, okay, no zeros there. Work is zero on the isovolumetric. And so if the gas doesn't expand. So that'd be vertical lines on our PV diagram. So that'd be like C to A. So C to A would be zero here. All right, so that's what I meant by find the easy ones. Find all the ones that are zeros. And it looks like we've got three of them that are zeros. So, okay. Now, I think the next easy one are state functions. Because state functions, it doesn't matter what the process is, the equation is the same. And the only one that's a state function in my chart, although I guess I could put a delta S here. Not part of the problem, but maybe it would be part of the learning. No, I might add that in there, just for fun. Why not? It's Friday night. We deserve to have fun. What could be funner than calculation in entropies on a Friday night? All right. I'm exaggerating, kind of. All right. So if we then look at our state functions, well, entropy is a state function too. I'm going to hold off on that one. Of these three, delta E is the only state function. And it is this NCV delta T. And so keep that in mind because you can use it even if you don't have a constant volume process. Now, one of these is a constant volume. The C to A is a constant volume, but the other ones aren't. But I'm still gonna use that here. So B to C right here is constant pressure, but I'm still gonna say, let's do this. Let me do the delta E from B to C. I'll put in the number of moles, which is 1. Also, CV, as we mentioned earlier, CV is the 3/2 R because they said it was monatomic. So this would be 3/2 R. And then the change in temperature would be the temperature at C, so 121.9, minus the temperature at B, which was 609.5. Okay, so that's going to go right here, the internal energy from B to C. All right, so grabbing my calculator here, I can put a 1 times a 3/2 times a 8.31 times 121.9 minus 609.5. And it's a negative number, negative 6,078. I'll just go to the nearest, and then this is units of joule, units of joule, units of joule. And if I do entropy, joule over Kelvin. Okay. So that's the energy, and it's coming out. And it makes sense if you go back to the PV diagram. Well, we're going to be going to a smaller volume. The pressure is going to stay the same, but the way to do that is you got to take energy out. You got to cool it down. Its temperature's got to go down, and that's what we see. We see it dropping from 609 to 121. It goes across there, and I can do the same logic from C to A. Now, if I do that, I'm actually going to get the same numbers. And hopefully you see that right here. Remember, all three of these have to add up to 0. So this needs to come out to be a plus 6,078. And of course, I think you can see it when you put in N for the number of moles. CV is 3/2 R. And if you put in the temperature at A, which is 609.5, and you subtract off the temperature at C, which is the 121.9, you'll see that these numbers are exactly the same, except for the order. So this is reversed. So this is a negative and this is a positive, and so all three of them add to 0. So this was kind of fun to mention, but not really necessary, because like I said, these three have to add up to 0. And so that's why I put the 0 there, and I knew that this was isothermic. So I really just needed to do one of these two, and I did this first one knowing what the second one was. And then for that matter, remember these two have to add up to that one. So that means this would be 6,078 joules of heat being added, positive, from the C to the A. So C to the A, we would add it. In fact, C to A is a constant volume, and maybe I'll write the formula on the next page, but you probably are beginning to remember. We still got a little bit of ways off to the test, but to do heat energy, you can do NCV delta T for a constant volume, and Q could be NCP for constant pressure. But coming back to this one right here, the C to the A is constant volume. And so we would be doing this calculation, which is actually the same calculation as the delta E, and which is true because delta E and Q are the same for the constant volume because the work was 0. Remember, delta E equals Q plus W. So if you have constant volume where the work is 0, these two are the same, and that's what that's saying here. Those two add up to that one. Okay, perfect. Now, again, just kind of working these out, let's look at the B to C. Now, this is a constant pressure one. And as I just mentioned, this would probably be a good way to do the constant pressure to find the heat. So I'm going to put in 1 mole, and the CP is 5/2 R. And since I'm looking from B to C, this would be the temperature at C minus then the temperature at B, which is 609.5. Notice it's a negative number. Kind of makes sense. We're going to have to be taking energy out. All right, so if I grab my calculator and go 1 times 5/2 times 8.31 times 121.9 minus 609.5, and come up with a negative 10,130 joules. Now, first of all, notice the negative sign. Okay, so negative 10,130. But also notice that it is a bigger number than was added when we warmed it, well, I guess it's right here, at constant volume, even though we get to the same temperature. So as we go from B to C, we've got to take out more energy. than just putting in C to A. See, C to A is a 6,000 and change. We needed 6,000 and change because all we were doing was warming the gas. We were making the molecules go faster. They were going from a speed that corresponded to a temperature of 121 to a speed that corresponded to a temperature of 609. And it took a little over 6,000 joules to do that. And you might think, oh, you got to take the same out when you cool it down from the same temperature B to C. But it's got to be more you got to take out, a lot more. Because when you go from B to C, not only are you slowing the molecules down, but in the process, your gas is shrinking. Your gas is getting compressed. You're doing work on it. And that work would normally warm up the gas, but you got to pull that out too. So the reason this has to be a negative and something much more than 6,000, the 6,000 part is just because you've got to slow the molecules down. The additional 4,000 is because you're doing work on the gas. You're giving it energy by doing work on it, and you got to take that out also. So we've got to take out 10,000 when we go from B to C, but we only have to put in 6,000 when we go C to A, even though we're going to be at the same temperature. Because it's a matter of that work part of the equation. Now, let me point out again, as I fill in this chart, these two have to add up to that one. So if you ever know two, you can get that third one. So if you take the negative 6,078, then you move that to the other side, so you add 10,130, you get a positive 4,052. And of course, it's positive because we're squeezing the gas. So again, from B to C, we're squeezing it. We're doing work on it. Okay. That's why you do that. You got to take out so much. And you only have a net drop of 6,000. If you're putting 4,000 in, you better take 10,000 out to have a net drop of 6,000. And so this is the total. All right, now the A to B, the isotherm, again, these two add to that one. So if we can just figure out one of them, we've got the other one. And we've done work at a constant temperature before. Maybe it's worth re-deriving, but we know that work is minus the integral of P dV. And for a gas, P is nRT over V. And the reason that step is useful for the isotherms is because, like any calculus problem, you want to simplify it by recognizing what factors are constants so you can bring them outside of the integral and don't have to worry about them in your integration part. So in my case, I chose to change pressure, which was not a constant, into temperature and volume, because temperature is a constant, volume is not, but temperature is, and so I can pull that out in front. And then, of course, better still is that then I have a dV with a V. And so if we integrate from some initial volume to some final volume, we have the work is minus nRT natural log of final volume over initial volume. So that's how we can get the work. So we've got the minus. Remember, the number of moles is 1. R is 8.31. Now, the temperature during this process, we've got to come back to the table, but from A to B, the constant temperature is 609.5. And the final volume would be the volume at B, which is 0.05, divided by the volume at A. And that's just a ratio of 5. So if I put this in, I guess I'll start with a -1 and then 8.31, then 609.5, then the natural log of 5, I get a negative 8,152. Now notice the negative. I like the negative. The negative means the work is leaving. That type of energy is leaving. And sure enough, from A to B, as any gas gets bigger, it pushes on something. Okay? Pushes on the atmosphere usually, but sometimes, like the air rifle one we did a while back, there the gas is pushing not only the atmosphere back, but it's pushing that little pellet in that air rifle to shoot the pellet out. Anyways, in this case, we're just pushing the atmosphere back. And so we are losing energy due to work. And so the negative sign is a good indicator. Which means you would have to add heat of the same amount in order for it to come out to be zero. Remember, these two have to add up to that one. So if that's a negative 8,152, this has to be a positive 8,152. These two right up to that. So as the gas expands, it's losing energy due to work, but it's gaining energy because heat is transferring in, and that's why the temperature remains constant. It always sounds funny to say heat is transferring in and the temperature remains constant, but here's the reason why. You're transferring heat energy in, yeah, but at the same time, you're losing energy due to work, and you're losing it at the same amount. And so it would be like, having a bucket with a hole in it, and you put a gallon in, but a gallon leaks out. The change is zero. There's no gain in the water level. Whatever it was before you put in your 1 gallon, it's still there because everything you put in leaked out. And so that's it. You're putting it in, and it's coming out at the same amount. So there's no change, and that's kind of like an isotherm. Now, I mentioned I might do the entropy, and I think I will here, but I want to answer the question before I jump over to the entropy, because now we can add all these together. And so we could say, okay, we're going to add from A to B 8,152 joules. Then as it cools down from B to C, we're going to take out 10,130. Then we're going to warm it from C to A by 6,078. And so overall, we put a net amount of 4,100. And notice that's positive. Because remember, these two have to add up to that one, which is going to be zero for a closed cycle. So this should be minus 4,100. Right, and then of course the 4,000, because that's exactly what comes out. And so we put heat energy in and work comes out. Now, that's maybe should be confirmed with this calculation. This should be a negative 8,152 and then added to 4,052, and sure enough, negative 4,100. So it does match and makes me feel good. Now, like I said, when I started this one, I thought I would go ahead and do all the, what we call the state functions, or the state of the gas, the pressure, the volume, and the temperature, and all these changes in energy, either state functions or non-state functions, and figure out what those numbers are. I was pretty convinced we could find them. I'm not convinced we needed to find all of them. We even threw entropy in here. And I know to answer their questions, we don't need anything about entropy, but we'll go that direction. But let's see if we can answer now their questions now that we have all this information. Okay, so let's look at A. So A says the net work done by the gas. Well, coming back to our chart, the net work is the 4,100. This is the net work down here, adding them all together. And so from A to B, the gas expanded, and so that was doing a lot of work, 8,000. But sadly, we were forced to complete the cycle to compress it again. And so we had to get 4,000 back. So the net was 4,100 joules. And since they use the phrase by the gas, not on the gas, you might argue that they are after how much work does it do by, that is, on whatever it's pushing. So the negative is because it left the gas. So it's not on the gas, but it's by the gas. So I think they want us to record that as a positive number. We'll look at the answer in a moment and see what they say. But they do say by the gas. So they want how much is leaving as a positive number. B, the energy added to the gas by heat. Now, again, I think they're talking about net here. They didn't say in a particular cycle. And as we saw in the chart, the net right here was this 4,100. So we added 4,100 joules because it did 4,100 of work. So when the gas went all the way around and got back to A, it's ready to start it again, and the net change is 0. That's what makes a useful engine, that it has a cycle. It goes all the way through and starts over again. And so if you can have a little heat added and work done, and it's coming out that, it really doesn't matter whether it's a little bit of work or a lot of work. What only matters is that if you finish a cycle and you're back where you started, you can just keep repeating it over and over and over again. So that's the idea of building something with a cyclic process. So we can, scale it up. We can just make more engines of them. If we don't like what one cycle does, we can do many cycles, or we can have many engines doing many cycles. All right, so I think that's the answer to A and B. C says the energy exhausted from the gas by heat. So if it's coming out of the gas and by heat, so this is the column for heat, and if it's coming out of the gas, oops, I shouldn't have wrote on there. But if it's coming out of the gas, it would be a negative. And so this would be the 10,130 is what comes out. And I don't know if they want me to report it as a negative, because if the energy exhausted by the fact that they use by the gas makes me think they want a positive number here, but not real sure. We'll see what they got. But that's what comes out of the gas. Energy exhausted by the gas as heat. All right, then so D says, the efficiency of it. Now, the efficiency is how much work did you get out compared to the heat energy you put in. And this might be the trickier of the problems. We know the net work was right here, and it's actually the absolute value. So this is 4,100 joules of work, what this whole cycle did, okay? But where you have to be careful is you want to make sure you include the heat, and only the heat that went in all of it. So coming back here to this column about heat, from A to B, heat went in, but also heat went in from C to A. So there's two places where heat is going in. So the total amount of heat would be the 8,152 and the 6,097 that went in, but not what came out, not the 10,130. Again, it's a comparison of how much work was done. So it would be all the works added together compared to how much heat went in. So only the positive heats. All right, well, then to get a number here, I'll do the denominator first. Here is 8,152, and here is 6,078. So the 14,230 is going to be the denominator. 4,100 divided by that number, and it looks like an efficiency of about 28.8% is the efficiency of this engine. And then, of course, it says, explain how this efficiency compares to the Carnot cycle. So in other words, if we operated the same temperatures in a Carnot cycle, what would the efficiency be? And of course, that's always a fun comparison, because we know the Carnot cycle is more of an academic cycle than anything else, but it's a nice one to talk about. It usually is too slow to make a practical engine out of, but it is the process that allows us to tell what efficiency we could get without violation, or just what we could get, because it takes into account the first and the second law of thermodynamics. So based upon these temperatures, the low temperature was the 121.9 and the high temperature was the 609.5. So if we use those high and low temperatures and built a engine that operated on the Carnot cycle, again, maybe not practical, but if we built it, it would be how efficient would it be? And this would tell us. So 1 minus 121.9 divided by 609.5. And that would be 80% efficient. So I would say the way this engine is built, the thermodynamic cycle that it's going through is nothing to brag about. It's, I'll call it 30% out of what it could be, and that's as high as 80%. So we're a long way from what it could be. I'll say it again. Notice we never could be 100%. All right, well, maybe I'll check the answers here. Let's see. Let's go call it the answer sheet. Chapter 22. This was number 50. Yeah?
Got it. Yep.
They match?
Yeah.
All right, so good. I'll take you guys' word for it. The match, I won't even look it up. But this will give me a chance then to show you one additional step, not really asked, but why not, is we calculate the interest. Oh.
What was the answer for part B 4100? On here they have 14.2 kilojoules. Yeah.
Ah.
They add together the 8,152 and the 6,078.
Okay, let me come back to the question. I think I read the question wrong then. So B said the energy added. Oh, I took it as net. Okay, my bad.
Oh, so it's just asking for Q.
So it's just asking for the positive numbers.
Yeah. Okay.
Yeah. Okay. So that would be when you added those, 8 and 2 make a 0, carry 1. 8 and 5 make a 13, carry 1. That makes a 2 and a 14. All right. So the heat added, not the net. Okay. Yeah, now you made me look here. So this would be 4,100. Good. This they got, yeah, this is the 14,200. Good. Good catch. C, this is just the what comes out. This is the 10,000, which, and they even report it with a negative. This is the 28%-ish. When they put 0.9, I put 0.8. And then they say 80%. Good. Nice. All right. Now, again, I hope I'm not wasting too much of your time here, but I thought, why not do one? They don't really ask.
That's what
they don't ask it, but let's go ahead and do the entropy.
Yeah.
And I'll come back to my chart here and use this as an opportunity to say the definition of an infinitesimal change of entropy is an infinitesimal change of energy divided by its temperature. So to get the change in entropy, we have to add up a bunch of infinitesimal changes. So that is, we have to do this integral. So let's do this integral for the process from A to B. Now, the process from A to B is an isotherm. And that means you can pull the temperature out of the integral because it's constant. And so you just end up with a Q over a T anytime something is a constant temperature. And I thinking way back at the start today, we did that problem with I think that was the first problem of the day, number 50, yeah, with the athlete. And we just treated the athlete as a constant temperature. And that's really what we have here. So I could then just put in, and go back to my chart, the heat that went in is the 8,152 joules at a temperature of 609.5 Kelvin from A to B. And so this would be 8,152 divided by 609.5. And so that would be an increase of 13.37 joule per Kelvin. So I'll put that in my chart. It's a plus, 13.37. Now, so there is the increase in the entropy. Now, this one's kind of an interesting one, too, because you guys were asking, how to visualize and understand entropy, which isn't so easy to explain, but it's any of your randomness or your concentration of energy. So notice it's an increase. So that means there is either more randomness, if you will, or there is less concentration of energy. And so A to B did not change its temperature, but it did change its volume. So I would say if I had a container that was kind of small, it's now one kind of big. And that right there is more randomness. They're just spread out in a bigger mass. They're not going faster. So they are not more random because they are going faster. They are more random because they're in a bigger space. If that makes any sense. Or maybe energy concentration would be a good one to look at this. They were here, now they're here, the same temperature. So the concentration was here, and now they are less concentrated. So that would be an increase in entropy, a measurement of the less concentration of it. Okay, let's talk about the B to C. And so I'll do change of entropy from B to C. Now, again, it's an integral of dq over T. Now, sadly for this one, the temperature is not held constant. The pressure is. But what that means then is I can put Q equals to NCP, and if it's infinitesimal changes, I'll put a delta T or a dt as in calculus, and then a dq. So what I'm going to do is in place of dq, put NCP dt and put it over the T. So when I do the integral, noting that the number of moles and Cp are a constant, then I just get an integral of T dt. And this kind of looks like the integrals we did earlier with specific heat, although now we're doing molar specific heat. In fact, we're doing the constant pressure molar specific heat. So let's see, this would be the number of moles, which is 1, right? Am I mixing my problems? Yeah, this was the 1 mole. Cp, we talked about way at the beginning. Remember, Cv, because it was monoatomic, is 3/2. So Cp would be 5/2. So this would be 5/2 R. And the natural log. And so the B to C, the final temperature is the 121.9. And the initial temperature is the 609.5, which, by the way, you can see in the math, since we're taking a log of something less than 1, this is going to be coming out negative. And of course, maybe you can also see why the entropy should be negative from B to C, because B to C, notice we are shrinking the volume of the gas. We're also lowering its temperature. Both of those are less randomness or a higher concentration here of energy. And so it's coming down like that. So anyways, I expect a negative number here, and sure enough, I'm going to get a negative number. Okay, so 5 divided by 2 times R times the natural log of 121.9 over 609.5. And so we're looking at a negative 33.44 joule. Put that in my little chart here. This is a negative 33.44. Now, as long as we're looking at a chart, you might have remembered me saying that when you're doing your charts here, you probably want to look at the things that are zeros and the particularly state functions. That's how we got this zero here. We said, look, it's a state function and it goes all the way back to where it started, so there's no change. Doesn't matter how it got there, it's just no change. And entropy too is a state function. So all three of these should add up to 0. So in other words, my 13.37, add to it a negative 33.44, I would need a plus 20.07 here in order for all three of these to add up to 0. And if this was a test, I probably would just leave that and move on. But I'm kind of curious if I calculated the entropy using a constant volume calculation, because that's the C to A, would I get that same number? All right, let's see. And let's calculate the change in entropy then from C to A. And again, doing this integral. Now, C to A is not a constant temperature, so it's not as easy as we did back here for the A to B, but it is nearly identical to the B to C. Remember, the B to C was constant pressure, and we just put in the equation for the molar specific heat. Now we can do the same thing, but we would put in the constant volume molar specific heat.
Is that like if you're solving for the entropy of an isothermic or an isobaric, are those integrals always going to be the same for an isothermic across all questions? Will that be the same equation?
Yeah. So the isothermal, you would always pull the temperature out and then just get this Q over T.
What about for isobaric and then isovolumetric? Will those always end up being the same?
Almost the same. One would have a CP in it and the other would have a CV.
Yeah, I mean, if you have an isobaric from one question and an isobaric from another question, they'll remain the same consistently across.
Yeah.
Yeah, that's fine. I just wanted to make sure.
Yeah, and then they look like this. They have an N, and in this case, it's a CV. Last time it was a CP. And the times before, that first problem you asked about, and we did the athlete who drank the water, then we were doing specific heat. So we had mass and specific heat, but we always had a natural log of final temperature over initial temperature.
Will you give us the value of R on an exam?
Well, it's open book, so I'm not going to give it. You can look it up in the book, or you can shoot me an email, and I would send it back to you.
All right. Okay.
Yeah. But yeah, In an open book one, I won't give it to you, no. But I won't not, if I can do a double negative, I won't not answer the question if you asked it either.
Mm-hmm.
Okay. And so if I put my number in here, this is 1 mole. CV, as we mentioned earlier, because it's monoatomic, is 3/2 R. And the natural log, and so we're going from C to A. So at A, it ends up at 609.5 Kelvin. And started at C, which was 121.9. And I'm hoping that kind of confirms my 20.07. So let's see what I get here. And so 3 divided by 2 times 8.31 times a natural log of 609.5 divided by 121.9, and within rounding, it's a plus 20.06 joules Kelvin. Yay! So, nice. Total change of entropy should be 0 for the gas.
I had a question about the integral you did, the first one with the isotherm.
Yeah.
The bounds were just 0 to Q, and I was just curious what the logic is behind those bounds. Does that make sense?
Yeah, I guess it wasn't so much as 0 as it was this. It was 1 over T, and it would be some initial Q to some final Q. And this is where I think we use terrible notation in thermodynamics, because this technically would be the change in Q. Well, all Q's are change. Q is how much heat did you add? So this is the Q.
Okay.
It really is. That's why when you write the first law of thermodynamics, to me, it always looks funny. You put a Q plus a W, and you set it equal to delta E. It just seems like there should be like a change, and the other change results in the total change.
Gotcha. So it was just the notation thing. It's just that Q is Q initial minus Q final. Okay.
Yeah. So Q, it's a little bit like we do that with time. You know, we often put T for time, but really it's always the beginning minus the end. It's just, where do you want to call 0 time? Yeah. So. Yeah. So I got the impression you were kind of worried about why call that 0. And I really wasn't. I was just saying it was the change in heat. Yeah.
Just how I was making the math work out in my head.
Yeah.
You got a Q.
No, yeah, no, that's good. Those are the kind of things that you exactly should be struggling with in your head right now and trying to straighten out. Uh-huh. And then in this case, it is just a not so great notation. Okay, well, we did way and above what that problem asked with the entropy, but I think that was good. Okay, I'll cross out number 54. The next one I got here is 39 on the list, although maybe in all fairness, should I jump over to the chat room? Is anybody screaming anything that wants to get done? Okay, good. There's nothing extra in the chat room here, so I will then say, let's go to the next one that was asked earlier. Number 22, or chapter 22, number 39. And what time is it? 3:59. Yeah, I spent 55 minutes on that crazy thing. All right. But I think it was good. All right. If it was good, you can't spend too much time on it. Right. All right. So let's me see what this one is. And this must be on the first missing page. Oh, this is a great one. Oh, yeah. And conceptually, it's hard, but it's actually pretty easy once you get past the conceptual idea. So, yeah, this one's actually probably a lot more physics than it is math. All right, let's try this one. It says 1 mole of a sample of hydrogen gas is contained on the left side of the container as shown in the figure, which has an equal volume of left and right. The right side is evacuated, so there's no molecules on the right-hand side. When the valve is opened, the gas streams into the right-hand side. What is the final entropy change of this gas? Does the temperature of the gas change? Assume that the container is so large that the hydrogen behaves as an ideal gas. All right, well, all of our problems we have been assuming it behaves as an ideal gas. So I'm glad they say that, but we have this PV equals to nRT. But there's an important, and it's more conceptual, that can really get overlooked. If you have a gas, let's say I have a gas trapped in this weird shaped object, and so I'll just say it's at some initial pressure. If you let it expand, we often say it does work. Now, why do we say that? Well, going back to physics 121, work is force times distance. Well, it clearly is expanding, so it's moving a distance, but also it's got to push something back. And if we just let it expand in the atmosphere, it pushes the atmosphere back. So a gas, does work. In fact, I over the break was cleaning off my keyboard. And I don't know if you've ever used those little containers that blow compressed air, or a compressor, or maybe propane, especially those small green tanks of propane. When they get low, you're letting the propane out, or in this case, I had this little container. Maybe you're familiar with it. I'll put it. Here's my dust remover. All right. But, when you open the valve here, when you push on it, oops, oh, this is the new one. Yeah, I finished off one. Now, there we go. But if I open it, this the pressure in here, expands, and it's got to come shooting out this nozzle, and it's got to push the atmosphere back. And as a result of that, it has to do work. And of course, as it's doing that, it's got to give up energy as it's doing work. Now, here's the reason I say that. This problem is a bit tricky in concept, because when we have a vacuum and you let the gas expand into an empty container, an evacuated container, or maybe if you think about this in outer space, it expands so you have distance, but you don't have to push anything. There's no force. Remember, work is force and distance. So I would say that in this weird scenario, that the work is zero. We don't have to push against anything. We can just expand all we want. We don't lose any thermal energy. In other words, these molecules don't move any slower. They're not pushing the atmosphere back. And hence, I'm going to answer the second question first. The second question says, does the temperature change? No, delta T is 0. There is no loss of energy. The change in internal energy would be the heat and the work. And in this case, we're not giving it any heat. That's probably obvious. But the one that may not be so obvious is we're not doing any work. This has a fancy name. We call this the free adiabatic expansion. because when you let things expand with no heat, that's adiabatic. But if they also don't do any work, we refer to this as a free adiabatic expansion. So the name isn't so important, but the realization of when work is being done, the concept of when the gas is doing work, it's not pushing anything, it's not doing work. Pushing the atmosphere is doing work. That's why it's kind of weird. Sometimes people will tell me that, hey, I have a gas and it just expanded. I mean, I just let it expand in the atmosphere. I didn't use the gas for anything, like maybe a pneumatic wrench or a pneumatic drill, or what else do we use compressed air for? A propeller on a underwater apparatus thing, all those compressed airs, and scuba divers will use them to pull themselves around. Anyway, that expanding compressed air spins a propeller. But even in the atmosphere, you still are pushing the atmosphere. So you usually still do work. But this one is not. This one is a free adiabatic expansion. All right. So temperature doesn't change. Now I can get to the heart of this problem. Remember, and we're glad we touched on it on the last problem, the change in entropy is the integral of ds, which is the integral of q over t. Okay. How do I want to say this? Let me doodle here for a second here. Uh, I want to say constant. Um, hmm. Yeah, drawing a
entropy right now.
Yeah. I want to do this entropy step, but what I'm trying to say here is if you could imagine the gas then filling up this container, so the volume's getting bigger, but the temperature is not changing. Mm-hmm. So this would be an expansion of the gas mm-hmm. without letting the temperature change.
Okay.
And so I want to write this as, what happened?
Oh yeah, it looks like you froze. Oops.
All right, let me go back to my screen share here. Looking for a clever way to say this. Let me put a pause on this equation here for just a second. Let me go to the first law of thermodynamics. Remember, the first law says change in internal energy equals work plus Q. Okay. Now, hope I'm saying this well. Let's dE would then be equal to dW plus dQ. Yeah, sorry, I might have to look at the book. There's a part of the adiabatic free expansion that has to do with just volume. There's a pressure change and a temperature change. How am I trying to? Not doing a good job of saying this. If I were to do this, if I would go integral of dq dt, let me write that. I'm going to try this. I hope I don't get myself lost. But this dq, I could write as dE minus dW over T. Now, dE, remember that's a state function, that the change in internal energy is NCV delta T. So if I write it in infinitesimal form, this is N CV dt. And this right here, the dW is minus P dV. Okay, hope this is working. Yeah, I think I'm going to get there, but I'm not sure this is the best way. Yeah, I can't think of another way. But what I was struggling with here is trying to say that the integral has a dq, but I want to change that from a DQ. So I'm going to use the first law of thermodynamics, and that changes it to a DE and a DW. That almost looks worse, but watch this. This would be NCV dt over T. That's the first one. Plus, I'm hoping this is the one that works right. I've got the two negatives make a plus. I got pressure over temperature. Let me write the ideal gas law here. PV equals to nRT. So this would be nR over V dV. Good. Oh, good. I like where this is going. Okay, now this right here would be NCV natural log of final temperature over initial temperature. And this would be NR natural log of final volume over initial volume. And on your other equations that I did, entropy, I actually never did this conversion, but the reason we need it for this one is I wanted you to see then when a gas changes its temperature and its volume, you can write out one term for the change in entropy, which has to do with its temperature, and you can have another term that is the change of entropy to its volume. Now, since I didn't say this very succinctly, let me just kind of summarize. Let me go back here. All right. So here's what I'm trying to say. I'm trying to say that when you go to calculate the change in entropy, you have to do this integral. And this integral looks like it should focus on thermal energy. And although that's true, we can get it away from thermal energy by using the first law of thermodynamics. And so this integral, instead of having a Q, has an E and a W. The advantage of that is when you work it out, you now have two pieces. And so now you can see that the entropy change comes from two reasons. Number one, the molecules change their temperature. But number two, the molecules spread out in space. For this problem, this one right here is 0. There is no change in temperature because we're not doing any work against it. But this one here is a change in volume. And it goes from its initial volume to twice its initial volume. And so this would be NR times the natural log of 2. And so if I actually put in the numbers here, now that I fiddled with this one way too long, what number was it? 39, what did they give me? They gave me 1 mole, and then the R is 8.31 joules mole Kelvin, and so moles would cancel off, and then the natural log of 2. And so this one comes out to be 8.31 times the natural log of 2. So there's an increase in entropy, but it's all because the randomness is, the additional randomness is created by the fact that they are spread out in a bigger space, it is not because they move at a higher temperature. And I tried to work it out, and I hopefully got somewhere in your mind, but I'm going to go back to your textbook. And I know that he worked this out, and now I'm kind of curious how he did it. I want to give you the equation here. Irreversible, reversible, work, efficiency, gas engine. Okay, so here's entropy. Okay, so here it is. He calls it the entropy change in a free expansion. And how do you get it so quickly?
Yeah, solution manual is really helpful sometimes.
Pardon me?
Oh, I was just making a joke because I looked at that one on the solution manual and it's literally just like an equation. And I'm like, well, it didn't really show us how we got that.
Yeah, okay. And that's kind of what I was getting at. So I'm just, I was going to share the textbook. Oh, looks like my phone stopped sharing. So maybe I will anyways. I was going to say, nah, probably nothing to be gained. But let me call up the textbook on my laptop. But it looks like equation 22.11 is his derivation. And this would be page 6. Is it 666? Oh, it's the devil page. Okay. No, that's not right. 629. Oh, I see. They've got one where the textbook and then one for the PDF. So it's 666 on the PDF, but it's 629 in the textbook. Let me make it full size, and let me come back to Zoom and say, all right, where is my textbook? I'll share it. All right, so I don't know if this is helpful, but that right there, 2211 is the equation that I kind of fudged with, but I've got the N, the R, and then the natural log of the difference in the volume. And I don't know if I should have just looked it up or worked it out. So I'm glad I worked it out, but it was kind of a struggle to get there. So hopefully I didn't lose you too badly.
No, it was good to see you work it out and break up that integral into the two individual parts. That helped me understand a little bit better, knowing that we can break that up into one that's like with respect to temperature and then one that's with respect to volume.
Yeah. Now, with that said, now that I look at the way he did it, I don't know if it's worth looking at it, but he did it a little different, and it seems to be a lot easier. Let me try what I think he did. Mm-hmm. He took this argument. He said, that when you expand it, you had an initial volume and you're going to expand it till it now has twice the initial volume. So he said on a PV diagram, you would be starting with some initial pressure and some initial volume. and you are going to expand it so that it doubles. It also would mean then if the temperature is held constant, this would be then an isotherm, and you would get half your original pressure. And so he makes the statement that why don't we calculate it using this integral, but doing an isothermal process. And he says that would be equaling to 1 over T because the temperature stays the same, and then a dQ. This is where I changed dQ into a dE minus a dW. But he took a clever approach that I'm debating in my mind, which is better. This is much shorter. So part of me says this is better. But he says, let's stop thinking of it as what it really is doing and treat it as the equivalent of an isotherm expansion. And the reason for that is because delta E equals to Q plus W for the isotherm. The isotherm has a 0. So he's saying the Q is the same as the W. Actually, the Q is negative of the W. But we had worked this out earlier by doing an integral of minus P dV to calculate the work. And that comes out to be nRT times the natural log of final volume over initial volume. So he just plugs that right in. He said this would be a Q over a T. But the Q is the Q for the isotherm. So he puts an nRT natural log of final volume over initial volume and then divides it by the T. The T cancels off, and he very quickly comes up with nR natural log of final volume over initial volume. And that was much quicker than me doing this integral. So the good part is it's much shorter. The bad part is you have to kind of make a mental change and say, I'm not thinking about a free adiabatic expansion anymore. Now I'm thinking about an isotherm expansion.
Mm-hmm.
And I can just use the Q over the T, and we already calculated the Q earlier on. Or you can go and do the integral and calculate the Q.
Mm-hmm.
I kind of like that. But
yeah, I don't know if I would have been able to like just in my head make that switch though.
Yeah.
Like I know how to do the equations and stuff, but understanding all of them like fully conceptually, like still not there. I don't think.
No, yeah, rightfully so. And this might be the hardest one on here because I don't know. There's some other hard ones too, but that's pretty clever. Yeah.
Cool. Thanks for going over that.
Still wondering why I didn't go that way, and why didn't I think about that first, huh? Well, I like both. Okay, so there you go. Both approaches. Okay, so let's see. I think there was another one on here. Yes, number 49. Let's give that one a try. All right, so chapter 22, number 49. And yep, see, I talk too much. Look at that. It's already 4:29. Me and wanting doing the entropy, and now see what the author did. Okay, so let's give at least this one a try for sure. And maybe I'll jump back over to the Zoom one. Did you guys ask anything more in the chat room? Okay, well, no more. So maybe we'll call this a day after this good one. All right. So it is chapter 22, number 49. Yeah, let me say again for you and anybody listening, although anybody listening might be a little too late by the time you get this, but you got to do a little bit of this each day because you can't just say, well, I'll spend 18 hours on it on Monday and I'll be ready for the test on Tuesday. It's not quite the same. You 18 hours on Monday, you'd be much better off to do 6 hours on Monday and 6 hours on Sunday and 6 hours on Saturday. And even then, 18 hours might not be enough. So maybe it's 10 hours on Monday and 10 hours on Sunday and 10 hours on Saturday. But you really got to spread it out. You can't just get it all in one shot.
Yeah, what about more like 8 hours a day, every day, beginning of the semester?
Yes, that's it, actually. That's ideal. All right, here. So let me try 49. Oh, good. This is a Stirling cycle because I did a diesel cycle earlier, and I know in the lecture we did the Otto cycle, and I also know in the lecture we did the Carnot cycle. So let's do the Stirling cycle. So in 1816, Robert Stirling, a Scottish clergyman, patented the Stirling engine. They are found in a wide variety of applications ever since. Yeah, they're really cool because the fuel's burnt on the outside. The problem with the internal combustion engine is all the moving parts are inside and the burning of the fuel is on the inside. I think that's why I kind of like steam engines. I like to see the old steam engine train go by. You know, the moving parts are on the outside and the boiling steam, you can kind of see at least where the cylinder is. But a Stirling engine is really neat because you just make a little campfire on the side and burn it and put a rod in on one side. I think I did this. Did I do the Stirling engine on the video? I hope I did.
Yeah, you did.
Okay, good.
It wasn't working too great for you. It was like being a little finicky, but you got it working.
Okay. So so you burn the fuel on the outside. So the fuel is burned externally to warm one of the engine's two cylinders. A fixed quantity of an inert gas moves cyclically between the two cylinders, expanding in the hot one and contracting in the cold one. Figure P2249 down below represents the model of the thermodynamic cycle. Consider N moles of an ideal monoatomic gas being taken once through the cycle, consisting of two isotherms at temperatures 3 T initial and just T initial, and two constant volume processes. I'll pause right there. Let me draw the PV diagram. And so the way the Stirling engine is built with the gas is, of course, it's a cycle, so I guess it doesn't matter where I start, but maybe I'll start with the twice the volume. And the volume gets compressed to an initial volume that's half as much. The whole time being at a constant temperature. So this is an isotherm. Then once it gets to this point, the gas gets warmed, and in an ideal setting, no volume changes. And so we go up to some pressure. Oh, they don't really say on the side what the pressures are. Okay. But they do say that it would warm up from, I'll say, an initial temperature to 3 times the initial temperature. Then this is where the work of the motor is done. The gas expands, pushing the piston, so it goes from the original volume to doubling the volume. And it does it while it's in contact with the hot environment, so it stays at the same temperature, although that's only really true if you run it slowly. That's why isotherms and the Carnot cycles are not really practical ones. This one has the isotherms as an ideal scenario. Then, of course, we right here drop the pressure by putting it in contact and letting it cool down, so the pressure drops, but at a constant volume. The old Stirling one, he would open and close valves, and so he would hold the valve, and so it would stay at the constant volume while things cool down, and then he could open it and let things move around. Anyway, so he would leave the valves closed while they either cooled down or warmed up, and then he would open the valve and let them expand into a bigger volume, or kind of trap them into a smaller volume. Anyways, but this is our cycle. So this is our Stirling engine here. And so I think I was just getting to the question. It said here, consider N molecules of an ideal monoatomic gas being taken once through this cycle, consisting of two isotherm processes of temperatures 3 T initial and T initial, and two constant volume processes. Determine in terms of N, R, and T, so we don't have any numbers to work with. A, the net energy transferred by heat to the gas. And then B, and so they said net. Okay, so B, the efficiency of this. The Stirling engine is easier to manufacture than an internal combustion engine or than a turbine. It's also lower on maintenance. It can run or burn garbage, so you just have to make a fire on the outside. So even waste heat, sometimes industrial plants that get hot and they have to use water cooling, you can just use the water coming out of a manufacturing plant. Like say they're building cars, but then you have this waste heat. You can then run a Stirling engine. And maybe use that to make electricity to run part of your plant, so you're not buying as much electricity. It can run on energy of sunlight and produces no material exhaust. Yeah, sunlight is really neat. We've got one of those. I know I didn't do it on video, but it's really cool. Sometimes I'll set it up out in the patio for the students, and it's got a big, about 1.5 foot diameter reflector that shines on one end of a metal rod. So one end of the rod gets hot and the other side stays cold, and it runs a little engine just from the sunlight. And so it's not a photovoltaic. It doesn't make voltage like photo cells. It actually just goes straight to heat and then uses a Stirling engine. So it's fascinating to watch because it's not as common. Well, anyways, let me kind of do the same thing with this one that I did on the other one. Hopefully I won't talk too long for you guys here. But if we kind of label these things as maybe starting here at A, going to B, going to C, going to D, back to A, we can kind of make a little chart for ourselves and say, all right, let's look at A to B. Then let's look at B to C. Then look at C to D. And then to complete the cycle, let's go D back to A. And then if we add them all together, we can even say, what is the total or the net of all of these? And if we put our delta E, our Q, and our W. Heck, and if we dare make more time, our delta S, why not? But if we then kind of look at this, let me emphasize my approach on these charts is to look for the zero stuff. So remember, the delta E is 0 during the isotherms, things that don't change their temperature. So A to B and C to D would be that. And also remember, it's a state function. So the whole process would give me 0 there for the net. So that's kind of what I would do first. Now, the Q is 0 during the adiabatic, and we don't have any of that. So I'll move on to the W, the work. The work is 0.
I think he might have froze up.
Oh. Okay. Let's see.
Isn't an 88 the adiabatic process similar to thermo process? Like on a chart wise?
Yeah, they look a lot the same. They
So
both.
how can you tell you don't have any ABD the A1?
Oh, the adiabatic, yeah, because they told me what they were. They told me that these two were isotherms.
Oh, okay, so if it's a curve in a problem, it would tell you if it's either A or the A1 or thermal.
Good. Yeah, good point. You cannot visually tell adiabatic from an isotherm.
Okay.
No,
So,
I guess if you put them next to them, you would do something like this. The steeper one would be the adiabatic.
but like in the test, you would tell us which one it would be.
Yeah.
Okay.
Or some kind of hint towards it. Like if I said, well, the easiest hint would be to say there was no exchange of thermal energy.
Okay.
Another hint would be the process happens really, really quickly.
So really, really quickly would be adiabatic, right?
Yeah, because thermal energy takes time. So it when, and that's why in the Otto cycle and what we did earlier, the diesel cycle, we said that the piston was compressing and pushing. So the compression stroke and the power stroke, both on the diesel cycle and the Otto cycle, we said, oh, take that as adiabatic. And we took it as adiabatic only because it happened so quickly. We know it can't be completely adiabatic because we know that the engine does warm up. We know that there is heat transferred from the gases to the engine. But maybe they're doing that more during combustion and not during the power stroke. Hard to know, but the power stroke, especially at 5,000 RPMs, is pretty quick. So there could be some thermal energy, but it's idealized is the word we keep using as no thermal energy.
Would I be right in saying when it's adiabatic, it's my Q that's equal to 0, and when it's isothermal, it's my delta E that's equal to 0?
Yes, exactly.
Okay.
Yeah. In fact, I think that's where my video froze. Is you right here?
I'm looking at your chart. I wasn't cheating. I was doing that by memory, but
yeah, right. So what I said, the delta E for the isotherm. So A to B and C to D were the zeros, and then that's when I think it froze right about here, where I said the adiabatic, the Q is 0, and we don't have any adiabatic, so I don't put any zeros there. And then the work would be 0 for any of the vertical lines, and we have 2 of them. And I think I just wrote the B to C when somebody said it froze. So the other one I need to write is the D to the A. And not really part of this problem, but we'll see if we throw it in here. The entropy then would be 0 for the whole cycle, because you get back to where you started, and the entropy is a state function. But there is no, all of these would involve some kind of heat, and so all of them would involve some kind of entropy. Okay. All right, so now maybe I'll start
if the
filling
delta,
it in. Pardon me?
sorry, if the delta E of a system is 0, is that always going to mean that my entropy is going to be 0?
No. Entropy is related to heat, not delta E.
Right.
But the delta Q is 0, yes.
Okay.
Yeah. Okay, so then what I like to do is the second option is the delta E is the easy one because it's a state function. So we know delta E is equal to N CV delta T. And I've said it a few times, but I'm going to say it again because it's kind of hard to see this, is that even if you don't have a constant volume process, you can use this. And 2 of mine are constant volume, and the other 2 are not. Although the 2 that are not, I already have the delta E. So I am going to use this in a constant volume process. But please remember, I would use it for any of these that would fit here. So let me try to find my delta E when I go from B to C. So this would be N. Now, CV would have to do with the number of degrees of freedom, and that would depend on the type of gas. And I thought I remember reading that they put an inert noble gas or something.
It was monatomic.
Monatomic.
So probably.
Okay. Stirling gas, Stirling engine found a wide variety of the fuels.
It says monoatomic in there.
Fixed inert gas. Okay.
About halfway down, it says an ideal monoatomic gas being taken once through the cycle.
Thank you. Yeah, okay. So they put inert gas, and that's why I was focusing my attention. But there they have it. All right. So the number of degrees of freedom is 3. So that would be 3R. And then this would be the change in temperature. So it'd be the temperature at C minus the temperature at B. Now, let me keep going because they want our answer not in terms of temperature. Or do they? Let's see, they gave us temperatures and volume. So I think I can use that. Okay, so the temperature at C is 3 times the initial, and the temperature at B is 1 initial. So that together is 2 times the initial, which would cancel with that 2. So this would be an N, a 3, an R, and a T initial, which traditionally we write the number first. So 3 NRT initial. So I'm going to put that right here. 3 NRT initial. Now keep in mind, the first law of thermodynamics is the energy one that says these 2 add up to that one. So that means this would be a 3 NRT initial. Also, keep in mind that these 4 have to add up to 0, and I know 3 of them. So this last one must be a negative 3 NRT initial. Okay. Now, again, maybe I'm doing more work than necessary. I wouldn't do this on an exam, but in terms of learning, this is kind of nice. I think I can fill all these in.
I think you're missing a negative sign on your Q for B to C. Shouldn't one of them be negative if they're going to equal 0?
Yeah. So I think the B to C is positive. And
I'm meaning for the work, right? Because B to C.
So these 2.
Oh, my brain is tired. Sorry, it's late in the day. Never.
Okay. Understandable. Yeah, so these 2 add to that one. So I think that's good. But yeah, keep me honest. Okay. Now, oh, and then I guess I could do the same thing here. These two add to that one. So this would be a negative 3 nRT initial. Now, the A to B are the constant temperatures, the isotherm. And we touched on this on that last problem where the author actually got the heat of an isotherm by doing the work, knowing that these two are equal and opposite. So let me just use that to our advantage. I'll label that as page 1 and come over here to a page 2 and say, if we wanted to calculate the work from A to B, and A to B is one of the constant temperatures, one of the isotherms, we would go minus the integral of P dV, and recognizing that both pressure and volume are changing, we would use the ideal gas law to substitute in for pressure, because when we do that, we get temperature involved, and temperature is a constant for this problem, so it can be pulled in front of the integral. And then we just got an integral of V dV, which then becomes minus nRT, and then the natural log of final volume over initial, which for us, coming back to our chart here, if I'm doing the A to the B, the final volume for B is initial, and the initial from A to B, so maybe I should have wrote this from A to B, so this would be volume at B, volume at A. So I'm integrating from A to B. So the final volume is initial. The initial volume, or I should call it the volume at A, is twice the initial. The initial will cancel off, and that would be a log of 1/2. Now, do you mind if I play a fun math trick? Why not, huh?
Do it.
I'm never crazy about logarithms with fractions. But remember that if you had something that looked like, this, the log of x to the n can come down in front. I call that the log roll. It can roll down off the exponent down in front of the log, hence the name the log roll. Okay, I'm going to do this. I'm going to take this negative, and I'm going to roll it back up the log and put it up there. So the negative's gone. And an exponent to the negative is the reciprocal, so that's just log of 2. And I like that better. Yay. All right. So
you got rid of 2 of my least favorite things at once. You got rid of a negative sign and a fraction. That was killer.
There you go. Sadly, you still have the logarithms, though. Those are the real killers.
I've learned to love logs. They get rid of hard stuff.
Yeah. Okay. Yeah, they're extremely useful. So I guess that's why they're part of our library of tools here. Okay, so this would be the work. So if I were to come back to my chart here on page 1, I can now fill this in as nRT natural log of 2. So that's the work from A to B. Now, if I also keep in mind the first law of thermodynamics, these two add up to this one, which is 0. So this must be a negative nRT natural log of 2. Which I am going to leave the negative. I'm not going to flip back the exponent. I want to see that they are the same and opposite. I think it looks better that way. Okay. Now, I'll run through it again, but remember, C to D is also an isotherm. So that means the work from C to D would be negative nRT integrated, starting at C and going to D of V dV over V. And so that would mean it would be a negative nRT, and then the natural log of the final volume at D, or volume at D over the volume at C. And I think in this case, since I don't have a fraction, I want to keep that negative. This will be the natural log, because the volume at D is 2 times the initial, and the volume at C is the initial. And so we would have a negative nRT natural log of 2. So if I come back over to here, then I've got a negative oh, and I do apologize. A to B and C to D are different temperatures. Bummer. So I put here nRT log of 2, and that's true, but I should have made one more step. I should have wrote this as nR, and then what is the temperature from A to B? That would be T initial. So I should have also put here that in the A to B, this could be written as T initial. And the reason that, of course, is important here is because right here, I've got the same equation, but I really don't mean it's the same number. This is minus nR, and this would be the constant temperature from C to D, which is 3 times the initial. And then, of course, the tradition is to write the number 3 first, then the nRT initial, then the natural. So keeping that in mind, then on my chart, I should write a minus 3 nRT initial natural log of 2. Which again, we're doing way more than we need to complete this problem. But these two add up to this first column. So this would be a plus 3 nRT initial natural log of 2. And so I filled in all the energies. And I'm still thinking it'll be fun to do the entropy here. So we'll, even though it's not part of the problem, we'll come back to that. But I want to make sure I do the problem. And so the problem would be then, if I were to add these all together, let me do the net here. So if I add these, this is a 0 and a 0. It looks like these are identical terms. They have an nRT initial natural log of 2. But this is a plus nR, and this is a minus 3 nR. So that's going to be a minus 2 nRT initial natural log of 2. And if I add these 4 together, I'm hoping I get a number so that when I add that to that, I get 0. So I'm hoping this comes out to be a plus 2 nRT initial natural log of 2. Let's see. And it looks like the second one here and the fourth one are equal and opposite. So they would cancel off. Yeah, and then sure enough, these are like terms. This is 3 minus 1, leaves it with 2. So it's plus 2 nRT initial. Yeah, good. Okay. So I have filled out this chart knowing way more than I need in order to answer their question. But like I said, maybe and hopefully more educational by doing every little box in this crazy chart. So let me finally get to the question, and so maybe I'll need another sheet of paper for that. But I can finally get to A, which A says, what is the net energy transferred by heat to the gas? Now, they said net. I just want to make sure because I didn't read it right on another problem. The net energy by heat. So back to my chart, this is the net down here. So they're saying this should be a plus 2 nRT initial natural log of 2. Let me just kind of check what they got. 2 nRT. Yeah, good. So we agree there. Good. B then says the efficiency of this engine. Okay, now there's a couple ways we can get efficiency. One is you can take the absolute value of the work divided by the heat going into the engine. I guess another way is you can change work into heat minus the cold one. And I guess a third option is we can simplify it to 1 minus the absolute value of the energy coming out of the engine and the energy going into the engine. I guess I just like this one. So why don't I do that one? All of them look like they're going to come out to be about the same amount of work to me. So let me start with the net total work. That's back in our chart. And the absolute value of that would be a 2 and an nRT natural log of 2. Okay. Now, if I divide that by the total energy going in, so notice it's not the heat energy, it's the things that are a positive. So it looks like heat energy goes in from B to C, that's a positive, and then C to D. And they come out on the other ones. But what goes in then would be 3 nRT initial. That's what's going in from the B to C. And then also going in is heat from the C to the D. So this would be a plus 3 nRT initial natural log of 2. And fortunately, there is an nRT in both terms in the denominator that when I factor it out would cancel with the nRT in the numerator. So in the numerator, I would have 2 log 2. And in the denominator, I would have 3 plus 3 log 2. So if I grab a calculator, maybe I'll do the bottom first. 3 plus 3 times the natural log of 2. Now the top would be 2 times the natural log of 2. I'll just take that and divide it by what I just calculated. And multiply by 100 to make it a percentage. And it looks like we are at 27.3% for this Stirling engine. And they're usually not all that efficient. And that would be, oh, a match. Good.
When you do efficiency like that, would you expect cancellations that would allow you to get an actual number?
Yeah, for in this case, because because for two reasons. One, the ends cancel because it's the same gas the whole time. And then number two, they listed all my temperatures in terms of the initial. So the final was listed in terms of the initial, and the final volume was listed in terms of the initial. So I would have expected all those things to cancel because it's a comparison then of just how many times bigger did it get? 2 times bigger, 3 times bigger, 4 times bigger. And those are numbers.
Cool. Thank you.
Yeah, so I expected a number here, and so I kept working until I got a number, not a symbol. And then I thought, was there a C to this?
I think there's just A and B.
Yeah, I don't see a C.
Okay. I thought maybe they were asking us to compare it to a Carnot cycle. And they don't, but I'm going to nonetheless. And so the efficiency of the Carnot cycle would be 1 minus the temperature of the cold over the temperature of the hot. The coldest one is the initial. The hottest one is 3 times the initial. And so that's 1 minus a third, which is 2/3. So, which is 66.7%. So if we were to use the same temperature difference and run a Carnot cycle, we would have double and then some more the efficiency. And so in terms of how efficient this is, it's not. And that's why I was curious about it. We could do a lot better with a different cycle. And Stirling engines often work that way. However, the real advantage of the Stirling engine is, remember, this is usually just waste heat. So this would have been heat that you would have normally just piped water up from the river, cooled your manufacturing plant, and dumped it back in the river, and you would have just been warming the river. So you might as well get something out of it. They're just what they call in the industry is waste heat. So
yeah, it seems like there would be an interesting design to start using these little Stirling engines at exhaust pipes of factories or something, just to like generate a little extra heat from whatever waste heat they're using or something.
Yeah, and that's been the new move in the last decade because every bit of energy counts, and it's very green. I mean, this is big. Yeah,
Cool.
It hasn't been a big deal since a decade, maybe 2 decades, but really more in this decade. All right, well, if you guys still want to bear with me, I'll do the entropy just for the fun of it. Let's see. What would be the change of entropy from A to B? Now, remember, all of our entropies are this integral of Q over T. The A to B is an isotherm. So the isotherm we had mentioned a few times already, and this just becomes Q over T. So in our case, if I go back to my page 1, my Q was the negative nRT initial natural log of 2. And my temperature from A to B was T initial. So they would cancel off. And so I'm going to get a minus NR natural log of 2. Let me think about the negative for a moment. From A to B, we're shortening up the volume. That would be less entropy. We're leaving the temperature alone. So in terms of their motion, there's not any more increase or decrease of their motion, but we are closing up their volume. In fact, now that I think about it, do you remember that equation that we did in the other problem, that NR times the natural log of final volume over initial is the change of entropy that has to do with volume change. And if you put in 1/2 of the volume and flip it up, you would get the negative out here and the 2 upstairs. So this equation, the 22.11 that I kind of derived the long way and then redid it the author's way, we could have applied that right here for the change of entropy, but I didn't. I did this. Well, which is how the author derived it. So I guess it is kind of the same. Anyway, so I'm going to put here that the change of entropy is a negative. It's the N, the R, and the natural log of 2. Okay. Now, as long as I'm working with constant temperatures, remember the other one, the C to D, is an isotherm. So in the isotherm, I'll just write it right here. The change in entropy from C to D would have been the Q over the T. The Q from C to D is a plus 3 nRT initial natural log of 2. And the temperature, the constant temperature of C to D is 3 Ti. So the 3 will cancel as whether the Ti, and we get a positive NR natural log of 2. So we get exactly the opposites. I don't think we have to, because it's all 4 of them that are supposed to add up to 0, not just 2 of them. But those are the 2, I'll say easy ones. I don't know if those are the easy ones or not. Let's find out. Because then, if I was calculating the change of entropy from B to C, this would be an integral of Q over T. The B to C is a constant volume one. So I can't pull out the temperature, but I can replace the dq with ncvdt, which then would come ncv and then a natural log. So if I'm going from B to C, a natural log of the temperature at C compared to the temperature at B. And then if I put in my numbers, N, CV is 3/2 R. The natural log, the temperature at C is 3 times the initial. The temperature at B is the initial. The initial would cancel off. And if I write my numbers first, I get 3/2 NR, 3/2 NR, natural log of 3. Now I get a positive. Let me just check that with kind of my thinking in my chart. So from B to C, there's no change in volume, but there's a huge increase in the temperature. So that would be more entropy. That'd be more randomness because of their temperature, not because of their volume. So sure enough, I do expect a positive number. Okay, so B to C, looks like I'd put here a 3/2 NR natural log of 3. Cool. Okay. Now, D to A, so change of entropy, D to A, is kind of that same thinking that I would do this integral and get NCV, and I'd get a natural log of final over initial, which in this case would be A and D. So this would be N times 3/2 R natural log. Temperature at A is initial. The temperature at D would be 3 TIs. The TIs would cancel. And you would have then a natural log of 1/3, which if you'll allow me to write it as 3 to the -1. So I can do my log roll and put the negative out in front. Oh, I'll even put the 3/2 out in front, and then I'll have the N and R and natural log of 3. So I can do that here. Negative 3/2 NR, natural log of 3. Good. And adding these 4 together do give me 0. They come in pairs, actually. The second and the fourth one add to 0, and the first and the third one add to 0. So they total add up to 0, as they should. Sweet. Okay. And 46 minutes. And did way more than the problem asked, but I think in a good way. I hope in a good way. Saw lots of really good examples. So we loaded it today. You guys rocked it. Stay awake any longer.
You're an animal, bro. Thank you.
Yeah, seriously. Thanks, Mike.
Thank you.
Oh, that was awesome.
All right, guys. Good. Yeah,
Have a
we
good
got some
weekend.
good ones on video. Can't wait to send these out.
Yeah.
I think it'll be helpful to a lot of people.
Thank you very much.
All
Have a
right.
good one.
Keep studying. Shoot me any questions if you got them.
I'm sure I will.
Yeah, same here. Have a good
All
weekend.
right. Take care, guys.